can then use to map out various structures in the subsurface. We have magnetic data, gravity data, electrical resistivity data. All of them are used to understand different properties of the subsurface. And then we have borehole and well log data to directly measure the properties of interest in the subsurface. We have all of these different modalities of data that people commonly work with in geophysics problems. So coming back to the picture I earlier presented about what is really happening when you're using a machine learning model, where every single component in the pipeline is being actively interacting with the human user. I think what I'm going to do now is describe some of the problems that are associated with each one of these components. So for example, when it comes to the data component, we know that one of the problems with the data set is that there is uncertainty in the human labels. If it is not accounted for, it leads to subpar model performance. So that's one of the problems that is associated with the data component. What about the model architecture component? Many times the model architecture does not account for the unique characteristics of the domain data. So that is another problem that is associated with that specific branch in this paradigm. With the training setup, sometimes people are not using the most optimal training configuration to extract the best value from the data. So that's one problem that is associated with this component. And lastly, with the evaluation and feedback component, there is lack of sufficient model transparency. So many users are not able to sufficiently trust the model because of this lack of transparency. There is also a high data annotation cost that makes it very hard and expensive to get enough labels by the human user to train the machine learning model with. Now, just to summarize all of these problems again, what I'm going to do now in the next few slides is look at how we systematically and specifically addressed each one of these problems in the context of geophysics applications. Starting with model architecture. A very common problem that geophysicists routinely work on is seismic inversion. That is basically taking seismic data and associating that with well logs to understand the properties of interest in the subsurface. So you have a seismic trace on the left, you have a well log trace on the right, you have a well log trace on the right, and then what I'm showing in this part over here is a seismic image, a 2D seismic image, and then below that is the property image corresponding to the same seismic image. So a very common problem that geophysicists work on involves going from this image to this image. Looking at the literature, there are two common methods geophysicists use to perform this inversion. The first method, commonly referred to as model-based inversion, involves starting with the model estimation, starting with a rough estimation of what the subsurface models look like. And then there is something called a physical forward model. The forward model is able to take in this subsurface model, this estimation of the subsurface model properties, and convert that into the associated seismic image. And then the seismic image is compared to the actual observed seismic using the recorded equipment in the field. And the difference between the two, the difference between the forward model seismic, referred to as X synthetic, and the observed seismic is then used to update the initial estimate of the model properties. And then by iteratively repeating the process, one is able to obtain an accurate estimate of the true underlying subsurface properties. With the machine learning setup, you have seismic data, and then you have well logs associated with certain points in the seismic data. So one would take all of the seismic traces and the corresponding well positions, and they would form the training data set for a machine learning model. And then this machine learning model would then be trained on this data set, And then afterwards, there would be the inference process where you take in the seismic data, the original seismic data, pass it through the model in a trace-by-trace fashion to collect, to reconstruct the properties at the other end. Specifically talking about the machine learning literature, the architectures that have been used to perform this kind of inversion, they're commonly based on multi-layer perceptrons, or recurrent neural networks, or convolutional neural networks. And I'll briefly talk about some of the limitations with each one of these different architectures. With multi-layer perceptrons, they're one of the oldest architectures that have been used to perform this task. But their limitation is that they're not able to model the temporal relationships in the seismic and the well log data. So they're not really suitable for this task. Recurrent neural networks and convolutional neural networks, they both perform better in this. They both perform better over multi-layer perceptrons in that they're able to model the temporal relationships between the different well log and seismic samples in the depth domain. But they're all restricted, but nevertheless, they are still restricted to only modeling the temporal relationships and not modeling the spatial context in the seismic. So what we proposed in this work was that in addition to having the temporal component, we would also like to model the spatial component. So you have a seismic image here in the plot here. And then I'm showing the seismic trace at one specific point in this seismic image. And then what we are saying is that if we only were to look at the temporal relationships between the individual depth points in the seismic trace and the corresponding well log, we would get a bad estimate for the output model properties. But if we were to incorporate into the seismic also the spatial context, we would get a much better estimate for the output quantity of interest. So the way we went about incorporating the spatial context while also maintaining the temporal relationships between the different depth points, we take a spatial patch of the seismic centered at the well position rather than only the well trace, rather than only the seismic trace at the well position. And then this patch is then processed by a special kind of 2D convolutional layer where the convolutional kernel is staying fixed in the horizontal direction, in the spatial direction, but it's dilating in the vertical direction. So in this way, this kernel is able to temporally model the seismic data, but it's also able to incorporate the spatial context into the problem setup. The data set that I use to demonstrate this framework is the popular SEAM data set. It has a corresponding seismic section that I'm showing on the left. It has a ground truth velocity acoustic impedance model that I'm showing on the right. And then I sample both the seismic and the corresponding property model for 14 equidistant well positions, And for each well position, I extract the well log firstly from the image on the right, the property acoustic impedance model on the right, and the corresponding seismic sample, which is really a rectangular patch of seismic centered on the well position from the image on the left. And then by collecting all of these pairs, I basically get my training data set. In this slide here, I'm showing the network architecture that I use to perform this inversion. So I have these 2D convolutional layers, the kind I described a few slides ago. And then these layers are broken up into 3 different blocks. The first block is called the feature extraction module, that is basically taking the 2D seismic patch and processing it to extract higher level features. And then the output of this block is going simultaneously into a regression module that is responsible for taking these features and estimating the well log property of interest. And then simultaneously, these features are also being passed through a second reconstruction module, which takes in these features and tries to reconstruct the original seismic. So this way, you get 2 different loss functions. You have from the quantity above, you have the well log estimation loss, which is the difference between the ground truth well position and the estimated well position. And you have the seismic reconstruction loss, which is the difference between the output well log, so the output reconstruction of the seismic and the original seismic. The reason I have the seismic reconstruction loss is to have a regularization term on the network so that it's able to learn better in limited data regimes. Here I show results for our proposed architecture, also compared to some of the other advanced state-of-the-art architectures in the literature. So in the image at the top left, I have the ground truth property model as before. And then on the top right, I have the prediction by the LSTM model, a standard LSTM model that is able to temporally model the different temporal relationships between the seismic samples, but not able to incorporate the spatial context. Similarly, on the bottom left, I have the predictions by the 1D temporal convolutional network, which is also likewise able to model the seismic data in a temporal fashion, but not able to incorporate the spatial context around the well position of interest. And then we lastly, at the bottom right, we have the proposed method. And it's clear looking at these 2D plots that the proposed method is able to perform the best at capturing the different regions in the original velocity model. I also show for these predictions specific traces sampled at randomly selected points in the original velocity model. So it can be seen in the different trace plots that I have here that the proposed 2D method is able to perform better compared to other 1D strategies at capturing the ground truth well position. And then we have a table comparing the different correlation coefficients between the predictions by the various methods and the ground truth. And it can be seen that the 2D TCN is able to perform the best when it comes to capturing the ground truth property. Next, I want to move to a different application, but still demonstrating the same concept of how the machine learning user can use their domain knowledge to guide themselves to make a better model to capture the quantity of interest. So in this case, the application that I want to talk about is that of seismic fault interpretation. Seismic images, like I discussed earlier, provide you a view into the subsurface, into the different layers and structures that are found in the subsurface. And then a very critical application that geophysicists are involved in is to identify the faults that are geological structures, a certain kind of geological structures on these seismic images. Faults are important because they form traps for hydrocarbons, and then by accurately identifying faults, one is able to obtain better drilling positions to maximize the oil and gas output from the survey. Looking at the literature for seismic fault interpretation with deep learning, you will commonly find two different kinds of approaches. You have the 2D fault interpretation that basically takes in data as either complete sections, 2D sections, or as patches of 2D sections. And then the model is trained on the labels provided by the interpreter on these sections, on these 2D sections. The advantage with this approach, with the 2D approach, is that it's very straightforward to train. You have a 2D model, you have 2D data. It's very straightforward to train a model on this data. Secondly, if you ever come across new data that you would like to incorporate into the model, it's also very straightforward to do that. You would simply take the new data, provide 2D labeled patches or sections from the new data, and simply retrain or fine-tune the model with this new data. The disadvantage with the 2D approach is that it does not take into account the complete spatial correlation in the seismic data, because seismic data, as it commonly happens in the real world, is a 3D volume. So if you're only looking at 2D patches, you're not looking at the complete 3D picture that is offered to you by the seismic data. So that's a limitation with the 2D approaches. When you come over to the 3D fault interpretation strategies, they basically work by taking in the 3D volume as small 3D chunks and then training the model on the labels for these 3D chunks. Now, obviously, a major limitation, needless to say, a major limitation with this kind of an approach is that it's not possible for a human user to provide you labels on complete 3D chunks of the data. So very often, what is commonly done is to synthetically model large quantities of training data in 3D chunks, in 3D cubes. And then these 3D cubes that are all synthetically generated, they're all synthetically modeled, they're able to train the network. So the advantage with this kind of an approach is that it's able to fully model the 3D seismic. So after you've trained your model on a synthetic data set, you can take it and afterwards apply on a real data. And it would be able to capture the correlations from all three directions in a seismic volume. The disadvantage with this strategy is that, firstly, it can only be trained on synthetic data, like I said earlier, because it's not possible for a human interpreter to provide you completely labeled 3D chunks. Second, the second disadvantage with this kind of strategy is that it's not straightforward to incorporate new data. So you have synthetically modeled synthetic data, and you have a network that is trained on this synthetic data. But when you move to a real data set, many times there is a domain shift that happens. And as a result, the model performance degrades. And to mitigate this domain shift, this performance degradation that happens due to domain shift, one would have to fine tune the model with the new data. But it's not straightforward to do that because the 3D CNN takes in input as 3D chunks or 3D blocks. But the interpreter is only able to provide you 2D images by way of labels in the new data. So there is this dimensionality mismatch that restricts the use of 3D CNNs on a wider scale. So how do we get across that? We basically propose that for a seismic section that you have where the interpreter maybe labeled a few sections for you, in this case, the section at the very at the top right, you would basically just sample 3D cubes from the seismic section. And then you would take the label section for the one seismic section that the interpreters did provide you labels for, artificially expanded to have the same dimension as the original seismic chunks. And then we use various computer vision strategies to basically make sure that the network is able to think that the 2D labels are the same dimension as the input seismic chunks. And using this strategy, we are able to train our network. In here, we show the results of this proposed fine-tuning strategy. So the column on the left is basically, the column on the extreme left is basically 3 different seismic sections from a real data set that we pass through a pre-trained CNN, pre-trained 3D CNN trained on synthetic data. It's able to get some of the faults, but it's also missing a lot of other faults. And then compared to the ground truth annotations that you can see on the extreme right. And then the column in the middle is basically our proposed fine-tuned CNN, where we take the pre-trained CNN on the left and fine-tune it with one single section from a real data set. So after we've done that, you can see that the results are much improved. Not only is the CNN able to find a lot of faults that were not originally annotated in the ground truth annotations, like the ones at the top, but it's also able to pick with better continuity the faults that were annotated by the interpreters in the ground truth annotations. So this brings me to the end of the section on model architecture design by the human user. The next component that I'm going to be talking about is where the user is responsible for efficiently designing the problem setup. Again, coming back to the problem of seismic inversion, oftentimes for seismic inversion, we are faced with the problem of very limited labeled data because wells are very expensive to drill. A single well can cost you several $1 million. So it's really expensive to obtain labeled data for seismic inversion. And what commonly happens with model architectures used to perform seismic inversion is the well-known phenomena of overfitting, where the model would do really well on the labeled data that it's been trained on, but any data that is not trained on, the unseen test data, it would do very bad on. So this problem can be mitigated by the use of transfer learning, which is a well-known machine learning paradigm, where you have basically wells that were taken in a different survey or surveys. And then by using the information from these other data sets, one is able to fine-tune the target model better to better generalize on the target data set. Now, the problem with conventional fine-tuning, but let me just, before I do that, I'll just briefly talk about what the conventional pre-training and fine-tuning strategy is. Using an example from computer vision, we have a large-scale data set like ImageNet that is used to train a network architecture like AlexNet. And then afterwards, one would take this pre-trained network architecture, freeze the earlier layers, and only fine-tune the last few layers on the target domain, on the target data set. The problem with doing fine-tuning, pre-training and fine-tuning, is firstly that you need a lot of subject matter expertise and trial and error to determine the optimal number of fixed pre-trained layers. So how many layers should you keep fixed, and how many layers should you fine-tune on the target domain? That's a big problem with the conventional pre-training and fine-tuning based strategy. Another problem with pre-training and fine-tuning is that sometimes the different domains, the source domain and the target domain, can be very different, can be significantly different. And if you perform transfer learning in this case, it's likely that your model is going to perform even worse than before if you didn't perform transfer learning, simply because of the fact that your transfer learning features from a very different domain to the target domain. Now, how do we propose to get around that? We propose a new learning paradigm that we call joint learning. And the way joint learning works, I have a simple toy example here on the screen to demonstrate how it works out. You have a data set A that is trained on a network A to output the quantity of interest on the labeled examples. And then if you were to train the data set, if you were to train the network on this data set in this fashion, on the simplified weight space on the right, you would probably get the network architecture to converge to some point that I call A. And then you have a second data set that I call data set B. You have a second network architecture that I call network B. And then network B is trained on data set B to likewise output predictions on the labeled data points. And then on the weight space, it would look like something like this, where starting at an initial point, the network is able to converge to some other point B. But what we are saying is that if there was some way to share information between the two networks, and I'll talk in detail about how exactly we do that, but if there was some way to share information between these two network architectures as they're also training on their respective data sets, what would happen in the weight space is that we would be putting a soft constraint on these networks to find solutions in the proximity of each other. So it's not a hard constraint in that the networks are forced to find the exact same spot, but it's a soft constraint in that they have to find two different solutions in the proximity of each other. It could be the same solution if that is what benefits the two network architectures, or it could be a different solution, or it could be different solutions. And the way we put this soft constraint on the network architectures to share information with each other is by using the L2 constraint on their weights. So we force their weights by using this L2 constraint to be similar to each other as they're also training on their respective data sets. The advantages with this kind of a learning paradigm is firstly that you don't need to set the pre-training hyperparameters as you would have to do with the conventional pre-training and fine-tuning strategy. You don't need to decide how many layers you want to keep fixed in network one versus how many layers you want to fine-tune in network one. Secondly, there is two-way knowledge transfer happening. So it's both networks that are benefiting from each other as opposed to only one network, which is what happens in normal transfer learning. Lastly, there is the case of negative inductive transfer that does not happen. So if you have the case where you have two very different data sets, if you were to perform transfer learning in the conventional fashion, you would probably end up degrading performance on the target data set. But in this case, because the networks, they have the room to find different solutions, you wouldn't have that negative inductive transfer happening because sharing information from two very different sources would cause a negative impact on the optimization function. So to demonstrate this paradigm, we go back to the original the SEAM data set that I demonstrated earlier. So I have the seismic for the SEAM data set. I have the ground truth model for the SEAM data set. And then I sample, as before, 14 different equidistant well positions on both the property model as well as the associated seismic as before. So the ground truth, the well log would be just the simple, would be just a single column at the well position. The seismic would be the spatial patch centered at the well position as before. And then we have 14 of these. So we have 14 different data and label pairs for the SEAM data set. The second data set that we have is another commonly used data set by the industry called the Marmousi data set. And likewise, we have the seismic as shown above. And then we have the ground truth property model for the seismic also shown below. And then for this data set, we sample a total of 51 different well logs. We sample well positions of 51 equidistant well positions. We would have the associated seismic patches, and then we'd have the well logs associated with these well points. So in this case, the seam would be the target data set because we have fewer wells for this, and also because it's a more difficult data set. And Marmousi would be considered the source data set in conventional transfer. If you were to perform conventional transfer learning, Marmousi would be considered the conventional source data set, and seam would be considered the conventional target data set. In here, I have the network architecture, which is the same as before. It's using the similar convolutional layers that are staying fixed in the horizontal direction. They're dilating in the vertical direction to model the temporal relationship. And likewise, it has a branch to output the elastic properties. It has another branch to reconstruct the original seismic. And then in this case, I have two different architectures. I have an architecture that is being trained on the Marmousi data set, and I have another architecture that's being trained on the seam data set. And they're both simultaneously training on their respective labeled data pairs. And also, as they're doing that, they're also sharing their weights with each other. So you have all these different loss terms governing the loss between the output quantity of interest, the seismic reconstruction, and also the weights between the two networks. And then the total loss is just a weighted sum of all these different layers. The weight on the third loss term is something that can change. If it is set too high, it is effectively like we're training a single network architecture on two different data sets. It would be effectively like that, as opposed to if it were set too low. In this case, we would effectively be training two independent network architectures on two different data sets. But if it's set to an appropriate, appropriate quantity, it leads to the scenario where the two different network architectures are training on their different data sets, but they're also sharing mutually beneficial information among each other as they're doing that. This here is the ground truth acoustic impedance model as before, and then on the right, I have the predicted acoustic impedance for the seam data set, which is the target data set in this case. And you can see that even with 14 wells, which is less than 1% of the complete data that is available, the network is able to perform well at capturing the different spatial and temporal correlations present in the data set. And then we have different quantitative metrics used to quantitatively compare the different strategies amongst each other. So in this case, like before, we are showing the well positions, 3 different randomly selected well positions, and how the predicted trace compares to the actual well trace. And is there a question? And then also for the table, it's showing the R-square correlation coefficient between the seam data set with weight sharing when it is trained simultaneously with the network on Marmousi data set, and also without weight sharing. So you have, and then same thing for Marmousi data set. So you have the R-square coefficient for Marmousi when it is trained with weight sharing versus the R-square coefficient when it's trained without weight sharing. And you can see that when the seam and Marmousi networks are trained simultaneously with each other, the R-square coefficient is higher versus when the two networks are trained independently on their respective data sets. That brings me to the end of the problem setup component. The next component that I would like to move into would be the data component, where there is uncertainty in the human labels that leads to subpar model performance. So we're going to look at if it's possible for the human user to model this uncertainty and then incorporate that into the training framework to better account for the problem with the labels that is commonly associated with geophysics applications. Again, bringing back the seismic fault problem, many times with seismic images and the structural labels on these seismic images. So in this case, I have a seismic image that I'm showing you, and there is also faults that have been annotated by a human being on this seismic image. So oftentimes, what happens with seismic interpretation is that the interpreters would only annotate the high confidence regions where they're sure of where the labels are. and they would leave unlabeled the low confidence regions. And this can be for many reasons. This could be because they're only interested in the targeted region that they perform the annotations on. It could also be because there's a lot of noise in the rest of the seismic image, and there's a lot of geological complexity that prevents them from determining accurately what the labels for that region should be. So there's a high confidence region where the interpreters are performing these annotations, and there's a low confidence region where they just leave it unlabeled. They don't label any structures of interest in the low confidence regions. Now, what we are proposing here is basically two different strategies to account for this uncertainty that is commonly present in seismic data. So with conventional strategies, the way they would normally sample data is they would evenly break down the seismic image or images into patches, into even patches, and then these patches would be fed into a network to train the network architecture. But the problem that you can probably see with this kind of a conventional approach is that you're getting a lot more, firstly, you're getting a lot more no-fault samples that have absolutely no pixels for the structures of interest, as opposed to patches that actually do have structures of interest. Like in this case, on the case in the left, you have exactly 2 blocks that have the structure of interest, and then every other patch that's taken on this seismic does not have the structure of interest. So you end up with this massive data imbalance, and that causes problems with optimization. The second problem with this strategy is that one is sampling from the low confidence regions where the interpreters are not actually sure of what the label is. And these patches would be contributing to the loss function, and this would lead to performance degradation for the network. So to get around this problem, we propose another kind of sampling strategy where instead of evenly breaking up the image into patches, we propose patching only in the proximity of the fault annotation that is provided by the interpreter. So in this case, one is always getting a patch that has some amount of fault pixels present, and secondly, one avoids the problem of sampling from the low confidence regions. And then the second approach that we take to model uncertainty on a pixel level basis, on a more granular basis, is for each seismic sample that we take from the original image and for its corresponding label, we have a spatial mask that basically penalizes the loss tensor based off the distance to the ground truth fault. So in the image on the right, you have a mask where the pixel values represent the weights or the emphasis for that pixel value in the loss tensor. So if there is a pixel value that is closer to the annotated fault, it would be weighed higher in the loss function, versus if there is a pixel value that is further away from the annotated fault, it would be weighed less in the loss function. So in this fashion, we are trying to maximize the contribution to the loss function from the pixels that we think are accurately labeled by the interpreter, and minimize the contribution from the pixels where we think there is more uncertainty present. And to demonstrate an extreme example where this happens, on the top, I have a seismic image that's been annotated by the interpreter for exactly one fault. So you can see a seismic image, and then there is exactly one fault that's been annotated on this seismic image. And on the bottom left, what I'm showing is that if I were to train my network on this seismic image in the conventional fashion, like it's normally done, what I end up with is a seismic image that has absolutely no fault predictions whatsoever. And this makes sense because of the reasons I stated earlier, because the network is seeing a lot more pixels that have no fault versus pixels that actually have a fault. As opposed to if you were to account for the uncertainty that is present in the labels using the approaches that I described, you get not only the faults, the original fault back, but also the other faults that were not actually annotated in the original image at all. So what this slide demonstrates is that by incorporating uncertainty into the training paradigm, one is able to have better predictions by the model, as opposed to if one were to ignore the uncertainty that is present in the labels. We are also demonstrating this fine-tuning approach with uncertainty, this uncertainty-aware fine-tuning approach on a different data set. So this one is from the Netherlands. It's in the proximity of Netherlands. We are showing 3 different randomly sampled seismic images and their corresponding labels on the seismic images produced firstly by the baseline approach that ignores uncertainty, and secondly by the fine-tuned approach that incorporates uncertainty. And again, you can see for each one of these images, the fine-tuned approach that incorporates uncertainty is able to perform much better at capturing the false versus the approach that ignores uncertainty in the baseline case. Lastly, I'm going to talk about the user evaluation and feedback component, where the human user is involved with looking at the model to make sure that it makes sense, the model predictions make sense, and secondly, providing input to the model to improve it. So talking about explainability and trust, why is it important for the model to make sense to the user is because it lets the user have more trust in the model. And I have here 3 different examples showcasing that, where having an explainable model can lead to more trust. So firstly, having explainability can let us allow us to debug a model architecture. You have an image of a dog here that you put into an image classification model to get a prediction. And in this case, what we are showing is that even though the prediction is correct, the model is looking at the wrong place to make the prediction. It's looking at the snow as opposed to the dog to make the prediction. So this is indicative of some kind of problem with the data set or the model or both. And this is one way explainability can help us with debugging model architectures. The second approach, the second method, or the second way explainability can help us is with helping us detect bias in the data set. So we have some kind of a crime control system that makes a prediction on some person. And then it turns out when you ask the model to explain its prediction that it was mainly looking at attributes of gender and ethnicity, which would be a problem if this system were to be deployed in the real world. So this is another use case for explainability in the context of machine learning. Finally, we have another use case for a loan financing system where the user data is fed into a loan financing machine learning system, and the decision is made to reject this person's applications. But what we really want for a deployable system is to also provide actionable insights for the user to improve their application the next time. So can this system provide recommendations to the user to have them improve their application for acceptance next time? So that would be another use case for explainability. Talking about explainable machine learning models, you have 2 major broad categories. You have machine learning models that are explainable or interpretable by default. That includes things like decision trees and rule lists, for example, linear models, where one can just look at the model coefficients or look at the model architecture to be able to understand how the model is arriving at a particular decision. But the problem with using the simple interpretable models is that there is a trade-off involved between how interpretable the model is and the model accuracy. So when you move to higher data sets, more complex data sets, more higher dimensional data sets, a lot of the times you would get less accuracy if you were to use an interpretable model versus a more powerful deep learning model that is less interpretable. So you have this kind of a trade-off involved. And this is where post hoc explanations come in. Post hoc explanations refer to the process of obtaining insights from a black box machine learning model after the model has already been trained on some data set. The general process would look something like on the slide, where you have a black box model. In this case, I have a neural network architecture that's been trained on some data set. It's fed into an explainer algorithm. And the explainer algorithm, it's able to locally approximate the behavior of the black box model in the neighborhood of some data point of interest using an interpretable model. And then by looking at this localized behavior of the interpretable model, one's able to understand what the black box model is doing in the proximity of the data point of interest. So the method that I'm going to be using in the context of geophysics interpretation is LIME. LIME works by taking a data point of interest and then trying to approximate the behavior of the original black box model by an interpretable model. And then it's able to do this by solving this kind of an optimization problem. The good thing with LIME is that it does not need access to the internal model workings of the original black box model. As long as it has access to the decisions of the model, it does not need to know exactly how the model works. And then it's able to approximate this model behavior in a localized fashion in the local neighborhood of some data point of interest with a linear interpretable model. The application that I'm going to be demonstrating for geophysics, where explainability can be used to help a geophysics application, is that of prospect risk assessment, where one has different well prospects and the associated data with the well prospect. And the task for the geophysicist is to look at all of these different attributes. And in here, we mainly divide them into 3 different categories. We have the initial probability of geological success, also called initial PG, that looks at different geological factors. We have the DHI index that looks at different data factors. We have the different quality factors. And by looking at all of these attributes, the geophysicist is asked to arrive at a final decision for if a particular well prospect, if you were to drill somewhere, would it be a successful prospect? Would it lead to oil and gas? Or would it be a dry prospect, for example? So for the data set that I'm using here, it has 300 plus well prospects, the decisions on well prospects, if they were successful or not, and also the associated attributes for these well prospects. The experimental setup that I use, I basically split 80-20 in an 80-20 fashion, the wells in this prospect. And then I train a machine learning model. In this case, I train an SVM. That is my black box model in this case, to achieve accuracies of 88% and 71% on the test and training and test data respectively. And then afterwards, I would be using the LIME algorithm to generate explanations for specific instances. LIME explanation outputs the coefficients for a linear model that is interpreted in the neighborhood of the data point of interest. So what you're looking at is one such explanation generated for one data point. On the left, there is feature names. There are substitute names for the different features that are present in the data set. And then inside the parentheses are the values that the feature takes on for that particular example. And then the bars denote the coefficients that are fitted by LIME, the interpretable model by LIME. Positive coefficients mean that for these features, higher values would correspond to an increased chance of success. And negative coefficients mean that for these features, having lesser values would increase the chance of success and vice versa. So higher values would decrease the chance of success. And then I'm showing these LIME explanations for 6 different instances in the test set. There are common patterns that one can derive looking at all of these explanations. So they're all local explanations. They're all basically interpretable models that LIME fitted in the neighborhood of these individual points. And then likewise, I can do it for the negative instances as well. So these are all of the points in the test data that prove to be a failure, where one did not find oil and gas deposits. And for these features, it's the other way around, where some of these features having lower values for them would increase the likelihood of failure, as opposed to other features where having higher, like the features with the positive bars having higher values for these features, they would increase the likelihood of failure, and lower values would decrease the likelihood of failure. We derive different functions to summarize these local explanations into one global model behavior. One of these metrics that we use is called the top K relevance score, that basically measures how frequently does a given feature show up in the LIME explanations for the top K rankings. And then by looking at the individual explanations for all of the different points in the test set and aggregating this metric for different features, we see we get this kind of a table where feature 3 is able to the feature 3 is coming out on top in terms of being very important in making a decision on a prospect, followed by feature 2 that ranks second, followed by feature 1 and 4 and 5 and so on and so forth. So by looking at this kind of a plot, one can try to get an understanding of how the model is globally interacting with the data set, as opposed to only looking at individual data instances. And by comparing what we know of these features in prior knowledge, it turns out that this is indeed the case, that these features do indeed matter in this order in terms of making a decision on different prospects. We also have another very interesting application where we show how we can detect a biased data set with using these local explanations. So we artificially introduce a feature into the data set called country ID, where for each well prospect, it has another feature denoting the country that it was drilled in. And then for 70% of the successful cases, we assign them to a single country. And the other 30% are randomly assigned between other countries. So what it results in is a heavily biased data set where the country feature alone is a very good predictor of success or failure. And then we train different machine learning models on this data set and then use line explanations as before to look at which features matter in terms of importance for these models. And I'm showing here in the left case, a data point that is negative, and in the right case, a data point that is positive. And in both cases, you can see that the feature that matters the most to the model in terms of making a decision is feature 27, which is the artificial feature that we just introduced. So this is one example where having these kinds of explanations can help us detect bias before we deploy the model into the real world. Lastly, there's another application that the user can provide interactive feedback to the model. So what we just looked at was a study where the user can ask the model for explanations on different individual instances. But another way the user can interact with the output of the model is to take the output and provide active feedback to the model. So that would be basically the next few slides that I'm going to talk about. The way I want to motivate is by looking at how difficult it is for users to interpret, annotate data, especially in the geophysical context. Because unlike the computer vision domain, you need a lot of expertise to be able to provide labels to geophysics data, unlike natural images, for example. So you need, firstly, there is the matter of the size of the data. We are usually dealing with tons of data. There is the expert knowledge that one requires. Sometimes it takes a lot of time to interpret these data. And then there is subjectivity, the matter of label uncertainty that we just looked at, that makes it difficult to provide annotations to such data. Licensing issues make it more difficult to open source this data to get more annotations, and so on and so forth. So specifically in the context of seismic volumes, we have all these different problems that I briefly touched on in the previous slides. There's the matter of size and resolution. Seismic data sets are very large in size. They're multidimensional. That makes them harder to interpret. And then the matter of multi-dimensional viewing, you can view them in different orientations. You can view them either in the cross-line orientation or the inline, or in the depth orientation. Multi-volume interpretation, sometimes you can have more than 10 different volumes for the same site. They're all basically coming from different acquisition parameters for the seismic setup on that site. Label subjectivity, something we already looked at before, is another problem that often happens with interpretation on seismic data. So the net result is that it makes it really difficult for us to train machine learning models on data for seismic, because we don't usually have enough labels to work with to train our machine learning model. Some of the other paradigms that one looks at in the literature that deal with limited data problems, we have semi-supervised learning. Fully supervised learning is the conventional machine learning scenario. We have semi-supervised learning, we have weakly supervised learning that basically both use some kind of label information, even if weak labels, to help the main task of interest. We have transfer learning, where we would be using labels from a different data set to help the main task and to help the target task. We have unsupervised learning. The main underlying assumption with all of these different learning strategies is that one already has all of the data set labeled, and then there is no further acquisition to be carried out. But what is not looked at in some of these, in a lot of these traditional paradigms, is that can we actually select only the most important samples to annotate even before annotation has happened, even before the annotation process has begun? Can we guide the geophysicist or the human user to only annotate the most relevant samples? And that's where we bring in the well-known machine learning concept of active learning. Active learning is concerned with taking a data set and only having the machine learning user label the most important points in the unlabeled pool. The idea is that you would get a similar performance to if you had the whole labeled pool, because these important samples that you provide the interpreter to label would be the most important ones. And then having the network only train on these samples would be equivalent to training it on the whole data set. So this is a motivation slide where I show how for different kinds of sampling scenario, we are able to obtain a high level of performance for the same amount of data using our proposed active learning-based sampling strategy. So I have the green curve at the very bottom, which is one kind of sampling scenario that geophysicists commonly use to annotate data. The orange one corresponds to a random sampling strategy where they would randomly pick data from a volume to annotate. And then the red and the blue are the active learning-based strategies. And we show that for the same amount of data, they're performing much better in terms of this performance metric that we have here compared to the other sampling strategies that are commonly used for geophysics tasks. This is a brief overview of what active learning looks like. We begin with an unlabeled pool of data. There is something called an acquisition function that points out the most relevant samples in the unlabeled pool. These are provided to the interpreter who annotates these samples, provides them to the machine learning model to train on. The machine learning model then updates the acquisition function, and then you can basically do the whole process again for a specified number of cycles. For active learning in the context of seismic interpretation, we use the theory of autoencoder manifolds, where autoencoders, as some of you might already know, they are a specific kind of model architecture that are able to learn the manifold of input data. So if you provide them some kind of input data, they'll be able to learn the manifold for the input data. And then once they have that, they'll be able to characterize the different samples that you provide them in terms of how close they are to the original input data. So if there is a sample, if you have some kind of a sample that is closer to the input data manifold, that would lead to a lower reconstruction error from the autoencoder compared to a sample that is further away from the input data manifold, which would lead to a higher reconstruction error for the autoencoder. So using this framework, we come up with this network architecture that is simultaneously taking an input. X in this case refers to an input, seismic data input, that is passed through an encoder network to get a latent representation. And then this latent representation is simultaneously input into a reconstruction decoder and simultaneously into a task decoder. So you have two different outputs coming from the same latent representation. One of these outputs, which is y hat, would be the output of interest. The other is just the reconstruction for the original seismic. And then by having the network train on these two tasks simultaneously, we end up with a case. We end up with a situation where the reconstruction decoder can point us to the most relevant samples that would be needed by the task decoder in terms of efficiency, in terms of sample efficiency. So this is the active learning proposed framework using this paradigm. We have at the top left, we have a network architecture that takes in a seismic image. It takes in a seismic image and simultaneously reconstructs the seismic image, and also provides the different rock labels on the seismic image. It's able to segment the seismic image in terms of the different rocks that are present on the seismic. In the second stage, one would take this trained network and then apply the reconstruction branch to the whole unlabeled volume to get a reconstruction score for every single data sample in the volume. In the third stage, one would sample the volume, one would sample the data point with the highest reconstruction score, because this is the one that is the furthest away from the manifold. So you want this data sample, you want the interpreter to annotate the data sample that is the furthest away from the manifold, and not this data sample that is already similar to what the network has. So the sample with the highest error is then sampled from the volume provided to the interpreter, also called the oracle. The interpreter labels the sample and adds it to the training data set. And then this training data set is used to train the network for the next round. And then the whole thing is then repeated for a specific number of cycles. We also propose a slight variation of this active learning framework, where instead of using the reconstruction error, we use the model entropy from the main task decoder branch. We use the model entropy. So that would be another query strategy to use for this active learning framework. The data set that we are using to demonstrate our active learning method is the popular F3 block, again, taken in the proximity of Netherlands. And then we have all these different strategies that I briefly talked about before. We have the reconstruction error-based sampling, where we are sampling the different samples from the unlabeled pool based off how far they are from the training manifold. Entropy-based sampling, where we are using model entropy to sample the most informative samples from the unlabeled pool. Random sampling, where one just randomly samples data from the unlabeled pool to provide to the interpreter. And then we have another strategy where we basically evenly divide up the volume into a number of evenly spaced sections. And these sections are then provided to the interpreter to annotate. And then once again, the curve from before. The proposed strategy, which is the autoencoder-based strategy, which is in blue, and then the red strategy, which is also active learning, but based on entropy. They are able to significantly outperform in terms of performance the other sampling strategies that are commonly used by geophysicists in the context of machine learning interpretation. And then one of the assumptions that went into this kind of a framework is that we are sampling based off the reconstruction error, but the task that we are really interested in would be segmentation. So is there some association between reconstruction and segmentation? And by looking at these error plots, it turns out to be the case. When you look at the reconstruction error plot for the different samples that are present in the unlabeled pool, and the segmentation error, in this case, the cross entropy error over the different samples, it turns out that the places where the reconstruction error is higher is also the place where the segmentation error is higher. So in practice, you would have only access to the plot on the left. You wouldn't have access to the plot on the right. But what we are showing here is that if you were to sample based off the reconstruction error, that would actually be a very good representation of sampling based off the ground truth error. And then we have this kind of an evaluation setup where we try to randomize the train test splits we use to demonstrate the effectiveness of the strategy, because it could be the case that by going with a simple training test split, with a fixed training test split, we are biasing the data set to perform better. It could just be that the way we divide the data happens to work for active learning. But by randomizing the splits, the training test splits over the entire volume, and then averaging the results for the different splitting strategies, we'll be able to get a more accurate picture of how active learning works out. So this here is, again, we have curves over the training split, which is, we should be more accurately called the unlabeled pool, because the actual training data is only a very small fraction of the unlabeled pool. So we have the training curves, training performance curves over the unlabeled pool, and we have the performance curves for the test split. And in both cases, we can observe the active learning-based strategies to outperform the baseline strategy for random sampling. And then we're also showing some visuals for the different model predictions. We have the ground truth prediction compared to the random sampling, compared to the reconstruction. And in both cases, you can see that the reconstruction-based approach, active learning approach, is able to perform better in terms of ground truth performance compared to the random sampling strategy. So these images are taken from the unlabeled pool that's used for training. And then these are from the test section. And also in the test case, we can observe the active learning strategy to perform better compared to the random strategy. So bringing the presentation to an end, I'd just like to review some of the points that we discussed. We looked at how geophysics interpretation can be looked at in the framework of a human-in-the-loop paradigm, human-in-the-loop learning paradigm. And then we specifically addressed different components in this human-in-the-loop paradigm. We looked at how the user can use their domain knowledge to better design models that leverage the spatiotemporal correlations in geophysics data. The user can use their problem experience, they can use their experience of the problem to design better training setups. They can model the uncertainty and use this uncertainty model during training to better account for uncertainty present in the model workflows. they can inject more transparency and trust into model decisions using the kind of explainability paradigm that we demonstrated. And then we can massively reduce annotation cost for the user with active learning by only pointing to the most relevant samples. And that brings me to the end of my presentation. If you're interested in reading more about some of these works, I have the references laid down here. We have journal papers, there's conference papers. They're also all available on our group website. So you're more than welcome to go to our group website to read up on these publications and also access the codes. And I think that brings me to the end of my presentation.
So thank you, Ahmad, for, telling us everything about geophysics. I think that's a very thorough understanding of geophysics and machine learning that we have received. So we are over time, and that's okay, but does anyone have any questions? And for the people that are online, I switched the microphone, so if you speak, we will be able to hear you. And for anyone here, if you have any questions regarding this, or if you just want to look at the papers and things like that.
I have a small question on the hardware use.
Hello?
Oh,
So I'll just address the.
so there's one question in the room first, but I did hear you. So go ahead.
Yeah, can you turn to that page?
Sure, sure thing. So for entity, what you have is something very similar to before, except that to get the method, the score, the uncertainty score that is associated with each training point, you would look at the output probabilities for each pixel. So remember, the output for segmentation would be basically a tensor. And for each pixel, you would get a vector equal to the number of classes. So for example, in this case, I have 6 different classes present in my seismic image. So for each pixel in the output image, I would have a vector, a 6-element vector that looks at the probabilities for how likely is it for this pixel to belong to each one of those classes. So I can use the entropy formula. I can use this formula to get an entropy score for that pixel, and then sum it up for all of the pixels in the image to get a total entropy value for the whole image. And by comparing this entropy value per image for all of the images present in the data, I can select the ones with the highest uncertainty. That makes sense.
Yes. You go to the previous page and just or the next, the one with the histograms.
Right.
Yeah. Model uncertainty. Actually, I was thinking, like, in my impression, if you have a more uniform distribution, you will have a higher entropy.
You're right.
Opposite of that. So
I think
I'm
I
confused.
got it down wrong there. I think it should be, yeah, like you said. Yeah, so if you have a, like
That's
a.
the probability thing?
Exactly. So if you have like a more uniform case, that means there is higher uncertainty present. And if you have the case like the one above, there is less uncertainty in the data. So we would like to sample the points that like this, that look like this, to maximize the model learning on the uncertain samples that don't already have similarity to samples in the training data set.
Oh, got it.
Yeah.
And to the person who was about to speak online, did you have a question?
Oh, yes. Yeah, thank you so much for a comprehensive talk. So, by the way, my name is Chuan Yiji. I'm from Telecommunications Group. So my question is, you talk about, for example, human intervention at all these stages for your problem. So after this may be a silly question to ask. So I was just wondering, at which stages you feel that human intervention would be most efficient?
Could you repeat the question?
I'm sorry?
Could you repeat the question? I don't think I got your question.
Okay, my question is, you talk about different aspects, different stages where human can kind of participate and then make contributions for your problem, right?
Right.
Yeah, so after doing all this, which stages you think human participation would be most effective?
Oh, so you're
For
asking
your,
me,
for your problem.
I see. So you're asking me so maybe if I can go back to the picture.
Yes, exactly. For example, data, you get model, you get, yes, exactly. So that will be this slide.
I see. So you're asking me, if I understood you right, among which of these components do I get the best value out of human interaction or the best performance?
Yes.
I think it's hard to say because like for each one of these components, the user is interacting differently.
Okay.
Like there's no like common ground, I'd say, between all of these different things. So for example, in the data component, the user would be responsible for modeling the uncertainty in the data and making sure that it gets incorporated appropriately into the problem setup. In the model domain, they'll be responsible for designing the model architecture that is best suited to the problem at hand. So looking at it this way, it's kind of hard for me to compare the two.
Okay.
Yeah.
Yeah. Okay. Thank you.
You're welcome.
Okay, so once again, thank you, Ahmed, for coming and giving your dissertation. It's really great work. You clearly have gone very in depth into understanding all aspects of it from this application viewpoint. So thank you again, and that concludes the CSIP seminar for this week. We will be doing this every single week for the rest of the semester.
Same time,
Same place. So yeah, all right. Thank you all. And that is it.